Hi there and welcome to the screencast for workshop 2 of 297 101 Statistical Data Science. So today we're looking again at ggplot2 and using that to visualize our earthquake data. We will be using another data set next time as part of your homework. The script we have today is exactly the same as the one we had last week. We will begin by just running all the code on it, and so I'm just going to select it all and hit run. That'll just load the data up and produce our first plot. Okay. And so today we're going to look at two things really. The first thing is we're going to look at some other geometries. So we've used the point geometry here. We're going to try some other things out. In particular, we're going to look at a smoother, which is a way to highlight the trend through the data. And then we're also going to look at labeling charts. Okay, so let's start by looking at another geometry. And we've already used another geometry last time. It was just sort of a little bit by stealth, and that's we used the geom jitter one, didn't we? Which added some jitter. But while that's another geometry, it's really just points in disguise. So to do jitter, we can actually use the point geometry and then specify a position argument as using the position jitter function. So that's an alternate way to do jitter. So we haven't actually really used another geometry. It's just the point geometry. So geom jitter is just a wrapper, if you like, around the point geometry, because basically jitter is something that you often need to do in the case of overplotting, and so there's a function for that. Okay. We'll start with a smoother. So we already tried geom jitter, but this is really just a wrapper around geom point, which specifies position. Right. We'll start with a smoother. So instead of geom point, we're going to switch to geom smooth. Okay, and we get a trend like this. So this fits a smooth trend through the coordinates of the points. The idea is that it highlights the trend of the data. So in particular, for each magnitude, that's the x coordinate, it is telling us what the average, it's important that it is the average, so that's the mean y coordinate is, so it would be the average stations, which is the y coordinate. That is the blue line. The grey band then, around the line, is a measure of uncertainty as to where the line is. So this is a key point with all statistical models, really. And this is fitting a statistical model. And the idea is that statistical models are not about, or are not directly about, representing the data that we have in front of us. Instead, what we're really interested in is the population that the data set that we have in front of us comes from. So it's not that we're just telling, we want to summarize things that's directly in front of us in the data, but in addition to that, we want to infer something about the population. So in this case, it would be we would be inferring something about all earthquakes in this around the country of Fiji, so in this area that we're looking at, and we're trying to say something about all earthquakes using the sample of earthquakes that we have, right? So when we do that, we need to recognize that we don't have all the information in front of us, right? We don't have the entire population. We haven't observed all possible earthquakes. And so there's some gaps in our knowledge that we need to fill in, right? And so therefore any conclusion that we make based on our partial knowledge, we've got to recognize is going to come with some uncertainty. Okay, and statistics essentially allows us to, in certain circumstances, to quantify the amount of uncertainty that we have, and that's what that grey band is doing. Okay, so the grey band is quantifying, so that's kind of the important bit, the amount of uncertainty that we have about what the trend between these variables are in the population that we can infer from our sample, right? So the idea is the sample is just a small piece of all possible earthquakes. So it can't tell us everything, but under some key assumptions, and the assumptions are going to be things like we have a random sample, and our model for the trend makes sense. We can use statistics and a bunch of maths to say something about those gaps, i.e. we can infer what the trend might look like in the population. But that inference will have some uncertainty, which is what the band represents. Okay, and you can see that the amount of uncertainty that we have varies, right, depending on the magnitude. So you can see that in the middle range here, we have very little uncertainty, right? The width of the grey band is quite small. Whereas at the top end here, at the higher magnitudes, we have a bunch of uncertainty, and that's simply because we just don't have much data up there, right? And it kind of makes sense, right? The more data you have, the more certain you can be that that data can tell you something about the population. Assuming, of course, the data are representative, which is the case if it comes from a random sample. And you can see here down at the bottom end, we also have more uncertainty. Okay, so this is why the uncertainty is so the uncertainty is higher at the ends of the magnitude distribution, as that is where we have less data. Having less data means we'll be more uncertain, right? So we can see easily here that there's a trend in that increasing size of earthquake results in more stations detecting that earthquake, which makes sense, and that trend is not really a straight line. Okay, so it's important to also show the data on the plot as well as the data summary, which is the smoother in this case, because the smoother doesn't tell us how much variation there is in the number of stations around the trend, right? It just shows us the measure of center. which is the mean, right? So we can do that by doing both, right? So we do our ggplot with our quakes, and then we add the points, and we also add our smoother. Right, so we can add multiple geometries to the same chart. So it's geom point, isn't it? Whoops. There we go. Okay, and so the advantage of this chart is not only do we see our trend, right? So we're highlighting the trend, but we're also seeing the scatter around the trend, right? So we can see that, for example, for a magnitude 5 quake, the sort of the range of the number of stations is anywhere from sort of about 20 odd up to maybe 100, with the average being at about 50. Okay, so the trend just tells us about the average, but of more use to us is also the variation around the trend, particularly if we wanted to, for a given magnitude quake, predict how many stations it would be at, right? We'd want to have a measure of the range that we might expect. Sometimes with these type of plots, it's useful to push the data into the background a little bit with some transparency. That's also important here because we've got overplotting, right? But we could potentially use jitter for that as well, right? So something like this chart here might be quite good. But we note that when we do this, we get some repetition in the code, right? So we can see that we've specified the mapping identically in 2 cases. And that's there's nothing wrong with that necessarily. It's produced the plot that we want just fine. But imagine the case where we want to adapt this code to a new data set. Right, so we might have a different data set, perhaps the penguins data set or one of the ones from your assignment, for example. And we want to adapt the code that we have that we know works for the quakes data to that other data set. Then when we think about what we'd have to do, we'd have to change the name of the data set to whatever our new data set is called, or whatever we've called our new data set. And then we would also have to change the mag and the stations to whatever those new columns are in that other data set. So in total, we'd have to replace 5 items here, right? And so there's 5 opportunities to mess something up in transferring this code from one case to another. And of course, 2 of those opportunities are just repeats. So it's, easy to make a typo. Okay, so we can reduce repetition by noting that the ggplot function also has a mapping argument. Whatever we specify there in the mapping argument for ggplot will be inherited by all the geometry layers. Right, so we can actually do the same plot by noting that we can actually put this mapping argument into the ggplot statement. And then we don't have to specify it in the point or the smoother, because they will then inherit the X and Y aesthetics. So that same chart is produced now with less typing, which is a good thing. But also we have the nice idea that we've reduced the number of places that we need to change the code for a new data set down to just 3 entries. So we had 5 and now we've got 3, so that's less opportunity to make a mistake. And also they're all on the same place, right? They're all within the ggplot function. So when we go from dataset to dataset, we just have to change things in one spot, which is quite nice. And so the kind of the generation of the plot, or at least the visual features of the plot, have been isolated a little bit from the source data, right? So the source data is kind of all input into the ggplot function, and then what the plot looks like then follows from there. Okay, which is kind of a nice separation between the data source and the code to do the plot. It means it's more transferable to another case. Okay, and sometimes, so with this inheritance, sometimes you still want other aesthetics to be altered on a per layer basis. So for example, maybe we want to colour the points by their depth, but we still want the smoother to be across all the data, right? And so we can do that by adding another mapping argument to jump points. Okay, so we can always add another mapping argument in to add other things. So for example, we could specify the color as depth. Okay, so now the points use the color. They also inherit the x and y from the ggplot statement, and then the smoother just has the x and y. Okay, now that's kind of important because the smoother is producing an average, and it doesn't make much sense to produce an average for different depths because the depth is actually a numeric variable, right? So potentially there might be 1,000 different depths because potentially each earthquake could have a different depth. Now I think the depth has actually been rounded, so there probably isn't 1,000 different depths. There's probably fewer than that, but nonetheless there are a large number of possible depths, and it wouldn't make any sense to try and fit a different smooth for each depth, because of course at each depth, if there's a couple of hundred different depths, then each depth would only have 5 data points on average, right? And fitting a smoother through 5 data points is kind of unconstrained, right? There's just not enough information in each one to fit a smooth curve. So we'd have to do that some other way. So what happens if we mess up and add color equals depth to the ggplot mapping? Right, so let's take it out of jump point and put it inside here instead. Then what's going to happen is this will mean that geom smooth gets the color aesthetic set as well, right? And when we run this, we see that we get the same chart, but you can see that we've got this error here. So we've got a warning message: the following aesthetics were dropped during statistical transformation, color. This can happen when ggplot fails to infer the correct grouping structure in the data. Did you forget to specify a group aesthetic or convert a numeric variable into a factor? So what's happening here is the smooth geometry knows that it can't work. It can't have different smooths for different colors if that color variable is numeric. But it can have different smooths for different colors if the color variable is a grouping variable, right? So for example, we could categorize the depth into 2 different depths, right? And then we might be able to do that. Okay, but we can't change the smoother for a numeric variable. So perhaps as a demonstration, so the warning message here is telling us that the smoother cannot do separate smooths based on a numeric measure. It can do a separate smooth for a grouping variable. So, e.g., we could dichotomize the depth into shallow and deep, and then use that as a grouping variable. Right, so just as a demonstration, this is not as part of the workshop, but just to sort of show you what we might do, we're going to take the quakes data, and I'm going to modify it by adding a new column, which is going to be how deep. It's going to be based on if the depth is greater than, let's choose a number, say 400, say. So if the depth is bigger than 400, it's going to be deep. Else it's going to be shallow. Right, so if I run that line, then you can see that I've got a new column added to the data, which is called how deep, and it's either deep or shallow depending on the depth, right? So here's one that's 42 kilometers deep, so that's a shallow one. Whereas these ones are 500 or 600, they're deep, right? And then if I so we're going to call that something new. Let's call it quake depth. Okay, we'll learn about this sort of thing, this mutate and so on later on. So now I've got a new data set called quake depth, which has that 6th variable added. Okay, and now I'm going to plot that instead of the quakes data. Right, so instead of using color by depth, let's do color by how deep. Then you can see that it quite happily plots, chooses 2 colors for the points based on that grouping variable, and it's also done 2 smooths. Okay. You can see that the trend is possibly the same, but that but it's been shifted up, isn't it? So the deeper quakes are felt more widely than the shallower quakes would be our conclusion based on this. Okay, so based on this, the deeper quakes perhaps felt more widely than the shallow. Okay. Right. Now, what is the smooth that we've added? How is it created? Okay. So let's go back and plot it earlier. Like we did earlier, we'll get rid of the perhaps get rid of the color. Okay. So you can see that it spits some information out. GeomSmooth is using method GAM with a formula y in terms of, that's what this little squiggle means, s of x, bs equals cs. So what does all that mean? Well, GAM, so the smoother is created using a GAM, which is a generalized additive model, where the y coordinate is computed based on a smooth trend, the S function, which uses cubic splines, the CS bit. Okay, so a cubic spline is basically a formula with a cubic, so that's with like an x cubed plus an x squared plus an x plus a constant term, and those cubics are local. So basically, we've got a different one at low magnitudes, a different one at medium magnitudes, different one at high magnitudes. So there might be sort of 10 different ones as you go from left to right, and they're constrained so that they're smooth, right? So that they smoothly transition from one to another. So there's constraints on the endpoints of each one, and on the how smooth they are, which is to do with the slope, and possibly even the second derivative, the curvatures. And essentially there's some constraints put on it so that it doesn't get too wiggly, is the idea. But that's a choice that the software has made for us, right? So the software under the hood has done some work to try and even out the wiggliness that you could have from a bunch of cubic splines put together. And we can demonstrate this by switching to a different smoother, which is a little bit easier to manipulate. So let's switch to a different type of smoother, a LOS or local linear smoother. Okay, and we're just doing this just to sort of demonstrate that there's a thing that we can modify. So we're going to say method equals LOS and span equals 0.75. All right, and so now you can see we've got a different shape. So the LOS smoother is not curling over as much at the top. Okay, and it's also sort of as a result doesn't really have the same bump in the middle here. Okay, so this is a different smoother made up of local linear fits to the trend. So what happens is that the data are basically sort of divided up into small regions of different magnitude, and for each magnitude, so magnitude 4 for example, we fit a trend through the data that use the information from the smaller magnitudes more than the information from the larger magnitudes. And so as we go up, we then constantly adjust the data that we're using. So as we look at magnitude 4.5 to get the slope there, we would use the information from magnitude 4.5. We would sort of weight that higher, and then we would perhaps use the 4.4 and the 4.6 and the 4.7 and the 4.3 and so on. And we would weight them less and less as we move away from the point that we're interested in estimating the trend at. So at the top end here, we're mostly using the high magnitude quakes to estimate the trend. Okay, so for each magnitude, we use information from the earthquakes around that magnitude to draw a straight line through the data. So we then so for each magnitude we get a different straight line which all link up to form a curve. Okay, and so the amount of data to consider for each of these local linear lines, local linear fits, is governed by the span parameter. Okay, so a smaller span will use data closer to, we'll use I guess less of the data for each fit, which will allow the overall trend to adapt faster to changes in shape. And a larger trend will use more of the data. So the overall trend adapts slower to changes in shape. Okay, so let's just have a quick look at how that looks. So if I specify a smaller span, say 0.4, then you can see that I've got a bit more curvature there. Right? So if I compare these two, you can see that it's adapting to the fact that it sort of needs to turn over in order to get down to this observation here. And it's also adapting a bit more down in here. You can see there's a bit of a bump down in here that perhaps you didn't see before. And if we make a larger span, so say 1, you can see that it's adapting less, right? And so it's we've got a much smoother shape through here, and it's more of a straight line at the end here. Okay, so smaller spans adjust to the data quicker. So introduce more signal, larger spans, smooth over the data more, so have a loss of signal. Okay, and so this is an example of what's called the bias variance trade-off. Is a key idea in statistics and data science in general that will come up again and again. The idea is that there's two ways for an inference about a population to be non-ideal. One is bias. Bias happens when we get things wrong on average. The other is variance. So variance captures the amount our estimator will change when the data set changes, e.g. when we get another sample. Okay, so there's two things that define sort of the quality, if you like, of a statistical estimator. And this smoother is an example of a statistical estimator because we're estimating the trend in the population. And those two things are that the trend that we infer from the data could be wrong on average. So that means that as we take many more data points or alternate data sets, the trends that we infer from those data sets might not be getting the signal correct, right? So for example, when we have a large span, if there is actually some detail down on the bottom here, such that that bump that we saw here, right? There's a sort of a little bump around 4.4 and some changes in curvature. Then if that's actually a real feature, then if we smooth too much with a span of 1, for example, then we lose that. And we're always going to lose that because we're always going to be over smoothing things if we use a too large a span. So we're going to get things wrong on average. Okay. Variance, on the other hand, is the idea that that we've only represented one data set here. And what might happen is when we collect a different data set, so we go out and we sample some more earthquakes, so we wait for another 20 years, say, and collect all the earthquakes that we observe in that time period, then of course these points are going to shift around a bit, right? So we'd expect the shape of the data to look kind of the same because they come from the same underlying population, but the exact location of the points will differ. Now, if our span is too small, and so we're adapting the curve to the data too quickly, then it's adapting to the particular quirks of that data set. And so some of the sort of the bumps that we might see in our trend might just be noise due to the sampling process. And so if we have two different data sets and compare the same smooth on each one, the smooths might look quite different, right? Because each of them are adapting a little bit too well to the data set that they've been trained on, if you like. Whereas if the span increases, right, so that we're smoothing more, then while we're losing some signal, those two smooths are going to look very similar between the two data sets, right? Because we're smoothing over the differences in the data that occur due to the sampling process, and therefore are sort of capturing the trend. The trend that we're capturing in each case looks very similar. So we've lost some detail, we've introduced some bias, but we've got less variance. Okay, and those two things, bias and variance, are always trading off, right? We've got this one parameter span that we can alter. If we make it too small, then we're going to, so if we make it smaller, we do better on the bias, right? Because each trend that we fit to a particular data set will be closer to the data, but we get worse on the variance, right? Each of them might get too close to the particular data set in front of them and therefore won't generalize well to other data sets. Whereas if we increase the span and we make it too big, then we might be missing features of the data, so we'll be introducing bias, so we'll have a loss of signal there. But when we come along and get another data set, those two smooths are going to look very, very similar. So we've got low variance, right? So small spans are going to have low bias but high variance. Large spans are going to have higher bias but low variance, right? And so somewhere there's kind of a happy middle ground for the span, which sort of balances those two things out. Okay, so small spans will allow the trend to adapt to the data quickly, so give us potentially more signal, so lower bias. But the trend from the low-S estimator might adapt too well to individual samples of data, and if we get another sample, the trend fit to that might look quite different. Thus, we have higher variance. Now, large spans will mean that we smooth over quirks in the data. So that smoothers from different data samples from the same population will look similar, low variance. But each of them will be missing detail, which introduces bias. So somewhere there is an optimal span value that minimizes bias and variance simultaneously. Right? So perhaps to demonstrate this, what we might do is we'll take some samples from these data. So let's take some samples. Right. So what I'm going to do is I'm going to take our quakes data and I'm going to add a new column, which is going to say our subsample is going to be okay, so don't worry too much about this code. Basically all I'm doing is I'm adding a new column called subsample, which is basically takes the numbers 1 through 6 sampled with replacement. So if I have a look at that just to see what it is, I've got this new column called subsample, and it just takes a random number from 1 to 6. So it's like I've thrown a dice, right, for each row, and therefore I've categorized each earthquake at random into 6 categories. Okay, so essentially I've divided my data of 1,000 rows into 6 different data sets of fewer. I guess on average there's going to be about 160 or 170 rows in each one, right? And so now I could take my sample and I could do a plot of just the first group. So what I'm going to do is I'm going to take my quake samples and I'm going to filter where the subgroup is 1. We'll be learning again how to do this a little bit later on. And then I'm going to do my point plot. So this is the data set. It's going to be equal to that, and then the mapping. So X is going to be the mag, and Y is going to be the stations. And then I'm going to do my points and my smoother. So we're going to use method equals low s, and we're going to do span equals 0.4, say. Right? It's called subsample, not subgroup. There we go. Right, so you can see here that I've got less data. Let's add some alpha again. Okay, and you can see now that the trend that I'm fitting is a lot wigglier. And that's because I've specified a low span. Okay, and now if I look at the second subsample, so if I look at subsample 2, so this would be like going out and collecting some more earthquakes and fitting the same type of trend, then you can see that the shape I get is quite different between the two. Right, the trend that's being fit is a little bit different between those two pictures, and that's because the data sets are a little bit different, and because we've used a small span, the trend is adapting to the specific data set I have quite strongly. Whereas if I change the span and say make it bigger, so that I'm adapting less quickly, then let's see what happens. So that's the adaptation, so that's the smoother on the first data set, and that's the one on the second, and you can see that these smoothers are closer to each other than the other two were. Right, so the variation between the blue line from sample to sample is less. But of course each one is not fitting the data perhaps as well as it should be. So there's bias introduced in that our trend that we're inferring for the population is not capturing the subtleties of the data quite as well. Okay, so we can see this all at once. So let's write some code that'll generate all 6 maps all at once. Again, we'll learn how to do this later. Haven't specified that. Okay, so here's all 10. Oh, sorry, all 6 subsamples with a span of 1, and you can see that the shape that we're getting here is roughly the same. Right, so the variation in the trend from sample to sample is small. So we've got low variance. But of course each one, because we've smoothed quite a lot, we're potentially missing detail in every single one of them. We're missing that feature of the data here where there's perhaps little bumps, that it's not sort of a smooth concave up, and that there's some little bumps in the data here in the general trend. If I change the span to something smaller, okay, then you can see that the variation between the trends is now a lot more, right? The shape of the trend is now quite different in some cases between the plots, but you can see that I am getting some more detail in each of them. Okay, so potentially these ones have lower bias, but of course I've got higher variance. And somewhere sort of in between these two things, perhaps around the default, we might have a reasonable balance, such that the trends aren't changing too much from subsample to subsample, but they are still adapting to the data so that we've got low bias. Okay, that's the idea of the bias variance trade-off. Okay, so let's just write a little bit about this here. Is that if we use a small span, then each of the curves are adapting to the particular data sets quickly, so are able to show us the trend well, low bias, but might be also picking up noise from the sampling process. So that they look different from sample to sample. Right? And then larger spans look less different from sample to sample, so they have low variance. But that smoothing over, but are potentially over smoothing some of the detail, which means we're losing signal and introducing bias. So there is a value of span that minimizes bias and variance. But determining that is hard or unsolved. Depends on the model type. So there are a bunch of things for different smoothers that do try and find that sort of happy balance between bias and variance. But it's typically dependent on the unknown distribution, so the unknown actual truth. So all of the estimators that we have, the properties thereof are usually dependent on the shape of the actual thing, which of course you don't know. So you often have to play around a little bit and sort of determine what you feel is an ideal span yourself. Okay, what else do we need to do today? I think we need to look at labeling our chart. Okay, so how can we add labels? So let's go back to the original plot. Right, let's just go back to our GAM so that we have everything original. So we can see here that these labels aren't awful, but they don't tell us everything, right? And so we can change the labels with the labs command. Okay, and the labs command takes the same, so the parameters that you supply the labs command are the same as the aesthetics. So if you want to change the x-axis label, you would change the x lab. If you wanted to change the y-axis label, you would change the y, and so on. So you'd say x equals magnitude, perhaps, and y equals number of stations, or something like that. Right? Would be one way of doing it. If you had color on your plot, so we could add mapping of the color. Right, then to change the name of the color scale up here, that's the guide for the color aesthetic, and so we would change the color label. So to give it a capital, well, we know it's in kilometers, isn't it? Okay, so we could do something like that. So in addition, there's titles and subtitles. So we could perhaps have earthquakes around Fiji as a title, which is giving us some context, right? Because I mean, we could perhaps infer that it might have been earthquakes because we've got magnitude here, but it wasn't particularly clear. And we also don't know where they were. So this title, while it isn't very exciting, is nonetheless telling us something about the plot. But we might want to add a slightly more interesting thing for the subtitle maybe. So we might be able to use that to help direct the reader to the take-home message. So the take-home message of this plot, of course, is that bigger earthquakes are felt more widely, right? So we might just say that. So larger earthquakes are felt more widely. Okay, we can also add a caption. So this could be chart by JM, right, which goes down here. Okay, so it's super important to label your charts. Obviously, you want them to be self-contained, right? So you want the x-axis to be self-explanatory, you want the y-axis to be self-explanatory. That doesn't necessarily mean that you have to have an x-axis label or a y-axis label. So there are cases when you can infer what the x-axis label is just fine based on what's written on it. So examples would be if you're plotting something through time and you have years or months or days, for example, the name of days is pretty recognizable, right? So if your x-axis has Sunday through Saturday, for example, on it, then you probably don't have to say that those are days of the week, right? That's kind of obvious. So you can make a choice not to have a label if you wish. So sometimes the label doesn't add anything. In the case that the label doesn't add anything, don't bother, right? Take it away. Because of course everything you add to the chart is things that aren't the data, right? And your focus should always be on the data and the story that you want to tell with that data. So you want to try and use your space on the page to maximize the size of the actual data in front of you. And so that's a choice to make when you do a title and a subtitle, right? If I didn't have the subtitle here, then the plot could be bigger, right? So there's always a trade-off to be made. But the general rule is make sure that your x-axes and y-axes are typically labeled. That's sort of the default. Put units on them so that they're sort of self-explanatory as to what the numbers mean. Write a title and potentially use that title as a way to focus the reader in on the story that you wish to tell. And finally, for the homework this week, we need to upload this chart. So we can export it by going Save as Image. Okay, you can choose where to put it by changing the directory. I'm just going to put it there where it is at the moment. You can change the file name, so my cool chart. Okay, and I can resize it as I want. Right, so perhaps I want it to look a bit like that. So I'm saving that, and that's now saved. So if I have a look at my files, I've got my cool chart .png, right? And then I'd go and upload that to Stream.